Information depth. One comment which sometimes gets remarked, okay, what is the information depth if I deal with different energies or different samples? The information depth really depends on the composition of your sample and what element you want to analyze. So there's not a common answer available, so you really have to see what is the matrix of your sample. And to give you an idea here, the dark one is steel, so it's a heavy matrix. The brighter blue is glass or stone, so like a geological sample. And the bright blue one corresponds to plastics or biological sample, for instance. For instance, if you want to analyze silicon in a heavy matrix, like metal alloy, the information depth for silicon is just 400 nanometers. For carbon, for instance, it's just around 100 nanometers, 150 nanometers. So there's always the question mark behind. If you can analyze an element on paper, it not necessarily mean you actually see it, because you may deal with conditions where you can't see it because the information depth is so low. In contrast, if you go to the other side of the element range, so if you go to tin K line, which corresponds to 25 keV, in the heavy matrix, the information depth is about 70 microns. So that means you get information, you see a tin K line up to 70 micrometers. If you have a geological sample, it's about 3 millimeters. And if you have a light matrix, it's about 2 centimeters. So keep this in mind. If you have a light sample and you are analyzing an energy line with a high energy, how thick your sample has to be, for instance, in order to be seen as an infinite thick sample. Primary filters. I just briefly want to demonstrate you the purpose of primary filters. Primary filters are nothing else than metal foils between the X-ray tube and the collimation device. And you see here, if you use different primary filters and you apply them to the primary spectrum, so for instance, the red spectrum, if you don't use any primary filter, so this would be then the primary spectrum emitted by the X-ray tube. And you see here, in this energy range between 7 and approximately 15 keV, you see a huge background, which may have a negative impact on your analysis. So what you can do, the strategy, how you can reduce the background, is that you can use different primary filters. And if you use then the aluminum, titanium, copper, so this is a sandwich filter, you see here, the background is really low, and it becomes then, it's starting then to increase beginning from 12 keV. If you see here this characteristic line, so this peak, so this is the rhodium L line coming from the rhodium target from the X-ray tube. Of course, this is overlapping with chlorine K line. So what you can do, if you want now to analyze chlorine, or if you want to analyze rhodium, for instance, how to get rid of this primary peak, rhodium L line peak, then you use the aluminum filter. So the red spectrum here is without the aluminum filter, and if you apply then the aluminum filter, you see how then the rhodium L line gets absorbed by the aluminum filter. So it's suppression of the characteristic line. Okay, another strategy why you use primary filters is you may want to improve the limit of detection. And here this is an example. So these are 2 coins. One is from 1899 and the other one is from 1816. And they are plated with silver. If you do the analysis of the coin which got minted in 1816, indicated here, you see there's a difference. So you see here a difference in the spectrum already in profile. But what you also see is that you have rather high background and you have some peaks here, a very broadening peak, and this is already indicating that you may deal with diffraction lines. So the another purpose of primary filters is to get rid of diffraction lines. And if you use then the aluminum filter, the heavy filter, you get then this spectrum here. And then you see really distinctive peaks, and you also see here fluorescence lines. And what you see here, so here you see a gold line, here you see a lead line and bismuth. which you don't see in the spectrum of the coin which got minted in 1899. So at 1816, the silver was contaminated by gold and lead, and in 1899 they already had the electrochemical capability to do a clean coating without the accompanying elements. This then can be used, in this case, you had to use the primary filters in order to reveal then the detailed information. And what really makes it interesting, so if the coins may look from the surface apparently the same, if you do then the analysis, then you can then see that one is the silver coating is contaminated with silver and lead, and the other one, which got minted later, doesn't contain these elements, these trace elements. Diffraction peak. So this is a property you don't like if you do XRF, in particular Micro-XRF, because a diffraction line can be misinterpreted as a fluorescence line. They can totally overlap a fluorescence line, and you always deal with this effect if you deal with structured material. Well, not all crystals, so this is just an extreme, so this is crystal, a huge crystal. You also deal with crystal structures in metals. In particular, if you have a microcollimated beam in combination with polychromatic excitation by an X-ray tube, it's very likely that you have diffraction peaks on structured material. And in particular, if you use a polychromatic excitation, the probability is very high that you may deal with diffraction peaks. So this is just an example. So the blue spectrum here is acquired with no filter, and you see a lot of very suspicious lines. And you already can assume that due to the broadening of the line, it's not a fluorescence line. But it's not clear here. So, and this is a sample where you may deal with a lot of different elements. So if you use then this sandwich filter combination, then the result is the dark red spectrum, which is way more cleaner here, where you really see then the distinctive fluorescence line. So what is a disadvantage, however, could be utilized. So if you want to, what would happen if you deal with a single crystal? If a single crystal has a constant orientation, you would see a diffraction peak always at the same position and the same height. If your crystal orientation is changing depending to the position of your sample, then the diffraction peak, the position may change and the height may change. And so this is illustrated here. So on the left side, this is a single crystal, and you see a homogeneous uniform color and intensity. Here you already see there might be a phase in between, because here you get different intensities. And the extreme here you see on the right side, so this is a polycrystalline solar cell, and each color corresponds to a different plane, orientation plane. So here this is very obvious that this is not a single crystal, and this is a single crystal. So you can use then, let's say, the diffraction peaks or the special distribution of the diffraction peak as an indication whether they deal with a single crystal or not. And here's another example. So this was a publication of one of our customers. He has used this diffraction plotting strategy in order to allocate and identify different domains, and this also during the crystal growth. So this helps them to get information about the crystal growth process and what kind of crystal you get at the end of the crystal growth process.